All right, welcome to Lab 3, our Gauss's Law tutorial. I'd like to start by talking about something that you've seen probably a bunch of times now in class, which is our random positive and negative point charges just hanging out in free space. Now in these situations, we've talked about electric field lines, which emanate into and out of. In fact, we define the positive charge as an electric field that emanates out, and the negative charge as an electric field that points inward towards the charge. And if you're going to solve that problem, you would probably just use the equation E equals kq over r squared, where q is the amount of charge of those point charges, and r is the distance away from that point charge. And if there's multiple point charges, you would just add up the vectors and so on and so forth. But what would happen if you had not just a few point charges, but a whole distribution of charges? What happens if you had an entire surface that was charged? I think it's a lot more complicated. You have to use some fancier math in order to be able to figure out the electric field at some distance away from that distribution of charges. And in fact, this is where Gauss's law comes into play. If we were to create an imaginary surface around this distribution of charges, I'm just going to make a box for simplicity, then you could calculate the electric field using Gauss's law. And let me show you how. The equation for Gauss's law is the electrical flux, the total electrical flux, which we'll get into in a second, is equal to the total charge enclosed divided by epsilon naught. Now, epsilon naught is the vacuum permeativity constant. It's just a number, it's just a constant, it's not going to change. Q enclosed is the total amount of charge that's enclosed by our Gaussian surface. In this case, if we knew the value of the total amount of charge in coulombs, we could just plug that number in and call it a day. The electrical flux is a little bit more complicated. It is a measurement of the amount of field lines that are coming out of that Gaussian surface. In fact, the electrical flux equation, as you've probably seen it in your calculus-based physics class, is the integral of the electric field vector dotted with the small area vector. But as good physicists, we want to simplify things as much as possible. And the way that we're going to do that is to try to pick a surface where the electric field through the area vectors is constant. As long as it's got a constant value through that surface, we can simplify this electrical flux to the electric field vector dotted with the entire area vector. And then we can find the electrical flux over every single surface and add them up and get the total electrical flux. Now there's one more simplification I'd like to make, because this is a dot product. We should probably turn it into the magnitude of the electric field through the surface times the area of the surface times the cosine of theta. Let me get into the vectors a little bit and let me describe to you what I mean. If I was to take the top surface here, the area vector is defined as going outward from the surface, which means that if I was looking at the bottom surface, it would be pointed downwards. But in this case, this area vector is pointed upwards. And let's say that our electric field was pointed at some kind of random crazy direction out from that surface. In this case, our theta is the angle between those two vectors. I'd call it theta there. Now let's talk about a few special cases here. For example, if my area vector here pointed upwards still, and the electric field was also pointed up, well, in that case, then the angle would be equal to 0, and the cosine of 0 is equal to 1. So in that case, we can pretty much disregard the area vector. Same thing again, area vector pointed up. What if the electric field vector was now pointed perpendicular to the area vector? Well, in that case, our theta is going to be equal to 90 degrees, and our cosine of theta is going to be equal to 0. And that kind of makes sense. We're trying to quantify the amount of electric fields leaving the surface. In this case, they're just running along the side of the surface, so there's no flux going through that situation. The last situation I wanted to talk about is what happens, here's our area vector again. What happens if the electric field vector is now pointed into the surface and not out of the surface? In this case, the angle between the two vectors is going to be equal to 180 degrees. In which case the cosine of theta is going to be equal to -1. So in the situation where the electric field is going into the surface, we would call that a negative flux. In fact, that's a good rule to follow in general. If the electric field is pointing out of the surface, then it's a positive flux. And if the electric field is going into the surface, then it's going to be a negative flux. So now tying this all back together, the electric flux is equal to EA. And I'll stick the cosine of theta in there, though most of the time we're going to create a surface where we can disregard that, is equal to the Q, the charge enclosed to the surface, divided by epsilon naught. And now you can start to see how knowing the charge enclosed can help us find the electric field, or maybe knowing the electric field can help us find the total charge enclosed within our surfaces. As long as we're picking our surfaces carefully, we can do some pretty complicated and interesting math. I'd like you to try problem number 1 on the tutorial. Come back after you're done and we'll talk more then.